So what we're going to do now is we're going to switch over to a live demonstration and show you how the tools can actually help us find some of these issues. Welcoming Eran, who's our VP of US support. So the first thing we're going to do is we're going to talk about a scenario with an RMA. So I'm an engineer, and I've just received information that we've received a returned part. Someone's placed that part on a tester. We've read the ECID, the electronic chip ID from that part. And what we want to do now is we want to, first of all, go into the database, bring up all of the historical information that the database has about that part, and not just about that part, but of course about everything that was being tested with that part. For example, all of the other parts in that same lot. And we want to look at that data and try and understand what the cause was. So the report that came up is a report that we call our unit level data report. It provides information across all of the operations for which this part was tested. We can see e-test or what, wafer sort, final test, and so on. And I can go in here, I can configure the report to also bring me all of the parametric test results and so on. So I can use that data either for this particular part or for the entire wafer or the entire lot to try and understand if I can find a signature that can explain the cause of this RMA. Now, I can also take this particular RMA and I can specify in the database that it is a returned part. Okay, we can filter and we can tell the system to show us just the RMA, and we can actually tell the system this is an RMA part, it was returned on such and such a date, I can give the reasons and so on. We can also expand the list of fields here. We can connect this to existing RMA databases as something we're doing now with a couple of customers, so that we can actually feed this information in automatically. The database now knows that this particular part was an RMA. Not only that, the database is also locking that data into the database. So from this point on, if, for example, our typical purging of parametric data would happen after, let's say, 6 or 9 months, depending on the customer's configuration, this data will no longer be purged. This lot has been marked. More than that, if the data has already been purged, which, as I said before, when you're talking about RMAs, the part could come back 2 years after it was manufactured, we can actually go back automatically to the data log storages and reload the data so that it's all available for the engineer to analyze. So again, within minutes of me knowing that a particular part has been returned, I already have all of the data I need in order to be able to understand what the problem is. And then I can unleash the full set of OptimalTest tools, for example, all of the rules that we have, the escape prevention rules and so on, to try and see if there's any signature for these particular parts which can explain why they were returned. What we've done is we've set up a rule. We looked at this particular data and we discovered, for example, that the rule that triggered for it is what's called the probe mark count rule, which catches that same issue that I was showing you in the presentation before. The probe mark count rule looks at all of the layers of data that we receive about each wafer or about each lot, and it determines how many times each die was touched. Now, this includes what we call hidden touches or hidden touchdowns. That's a situation when you're doing parallel tests, for example. You've got a probe card which touches 4 die at a time. But during a retest process, you're only going to see in the data log information about the bad die. You're not going to see the fact that that probe card was actually touching all of the other die that are under its pins at the same time and causing damage there. So the rule has all of the logic to be able to determine all of that. We've set up a rule. The rule has triggered. I've received an email. The email gives me all of the information I need to know about which wafer, which lot, at which facility it was being tested, test program, and so on. And if we scroll down on this email, we can see that we have all of the information also about exactly which XY coordinates triggered the rule. We can see that the rule was set to a limit of 8 touchdowns, so we have some die here that were touched more than 8 times. And of course, it's triggering only for good die. Okay, if a die is a bad die, it doesn't really matter. The problem is with the good die. Now, we have a link in the email which enables us to automatically launch the OT Portal application, which is the same application in which we discovered the problem originally. And when OT Portal launches from one of these links, it actually brings with it the data that's relevant for that particular alarm. So in this case, we have a wafer. The system automatically brings up the wafer. What we're seeing here is not binning information. What we're seeing here now is the touchdown count information. We can actually see which parts have been touched too many times. Okay, and in addition to that, if we look on the left-hand side, we can see very clearly that there were multiple executions of this wafer. It was run or resorted many times, and we would like to really try and understand why. So the system brought up a wafer map. It also brought up another unit-level data report. That's that same report which gives us all of the raw data about a particular wafer. We're just going to add in the probe card information as well to this report, because we can select which fields are displayed, and we're going to run it. You can see the speed at which this data is brought up. So now I have all of the test information for all of the parts across all of those different runs for these particular die. We can sort this information by one or two fields. In this case, we're going to sort it by X and Y. So now we can clearly see we filtered it down to the specific units that are failing. And we can see, for example, this unit with X, Y coordinates 10, 12 is good bin. We can see false. It failed over and over and over and over again. And eventually here, it received a bin 16, which for this particular product is a good bin. And if we look at the data, we can see very clearly that what actually happened is that someone switched out the probe card. In other words, some operator on the test floor was going against the instructions that they had been given. They was told probably only to test this wafer once or twice. They had too many failures. They were testing it over and over again. Eventually, they went and switched out the probe card. And hey, presto, they had great yield. But of course, in doing so, they completely damaged the parts that they were testing. And these are parts that you no longer want to send off to customers. So we saw the email. We saw how from the email we managed to get to the data in OT portal. Now let's take a look and see how we'd configured that rule to provide that email. How was the system configured to enable that capability? So we're now looking at another product called OT Rules. OT Rules is the application that you use to define rules, which can either provide alerts when something is going wrong, or even perform online action. So we have offline rules and we have online rules. Online rules, for example, can cause a tester to pause, or they can perform other actions that involve changing the flow of the test program. Someone asked before about adaptive test. Test time reduction is one area where we actually make changes in real time to effectively to the test program. We have many, many rules already in our library, and these rules have been built together with our customers based on the issues that seem to be common across the industry. And there are different types of rules. For example, yield monitor is a simple rule that looks for situations where a wafer's yield is significantly higher or lower than other typical population. We'll look at that one a little bit later. The S2S, or site-to-site rules, are ones which deal with parallel testing, issues with parallel testing. Then we've got everything to do with escape prevention rules. For example, probe mark count is the rule that we've been talking about now. Passing test with out-of-limits result is the example we saw before in that presentation. There's more complex stuff, for example, test list comparison between test program revisions. Whenever a new revision of a test program comes out, we can compare and provide the engineer with information about the delta in the list of tests so that the engineer can understand if, for example, he might have commented out some tests or too many tests, a typical issue that we've seen in many places. And then there are more complex rules, for example, all of the outlier rules, the classic outlier rules such as geographic part average test, GPAT, the more complex rules such as NNR, nearest neighbor residual, and so on. We have a very, very significant library of rules. What we're going to do now is we're going to take a look at the particular probe mark rule that triggered the email that we saw before. In this particular case, or for every rule we define a population. The population defines which product or which data is relevant for this particular rule. Now, you can define the population as tightly as you want. You can you can even set up a rule for a particular product or sub-product or a particular test program. You can also define rules extremely widely so that a single rule can actually monitor everything going through the database. And again, we'll demonstrate that a little bit later. In this case, we've set it up for a particular product because we wanted to use this on demo data to show an issue. If we go into the configuration of the rule, so a rule has a name, it has a description. In this case, it has various different types of limits which monitor the different ways a prober can impact or damage sites. Here we've set it up with a touchdown limit of 8. And down here we have the actions that the rule will perform when it's triggered. So the basic action is the engineering alarm. We're always going to send, or almost always going to send an email to someone when an alarm is triggered, because it obviously means that someone has been doing something wrong. But in addition, we have the more powerful capabilities. For example, enable bin assignment. Okay, as I said before, the product is integrated into the subcons, into their wafer map flow. So when they send the inkless wafer map, or before they send the inkless wafer map to assembly, we can intercept that wafer map. and we can perform bin switching. We can turn those good parts, which were tested too many times, into bad parts and prevent them from getting assembled. So even if the engineer is on vacation and hasn't received that email, okay, those bad parts will not reach a customer, and that's a really key feature. Another thing that's important to point out about that whole solution is that getting the rule back to the test house, or the internal or external test house, is all completely automatic. In other words, as soon as a user has created a rule like that, they can activate it. The activation process goes through a publication process, which sends the rule to the subcon completely automatically. The whole thing is it's a very smooth operation. It's a very easy to operate operation. Now, I've created a new rule, and I want to make sure that that rule is not going to over or under trigger based on historical data. And someone asked that question during Craig's presentation. We have a rule simulator which can take historical data. You can set it up for however much data you want. You can select the population. You just click select all, choose all of the lots that you want to simulate on, and run simulation. We've done this demo a couple of times in the last couple of years here at ITC, so we'll save time now and not go through the whole rigmarole again. But that would simply generate those same emails again, or just generate data in OT Portal, which I could then go in and view to understand whether or not those rules successfully caught the issues that I was looking for. So that closes the loop, really, with the touchdown rule, the overprobing rule. Another rule that we dealt with was the freeze rule. We showed you the example in the slideshot. This is how the portal view from that particular rule looks like when you open it up. So the problem occurred. It was caught immediately. The user received an email. He can go into OT Portal and immediately understand what the root cause of that problem is. And from here, of course, we can use all of the capabilities of OT Portal, which we just demonstrated in previous years, to drill down, try and understand, for example, the bin Paretos for these particular products or test programs, and try and understand the core issue. Right, you can go all the way down to individual parametric measurements, of course. Okay, so that's just another example there of the way we can run rules in real time or near real time in order to catch escape issues and prevent bad parts from reaching customers. But one of the areas where things get really interesting is when we're trying to take data across multiple operations and learn from that more about our testing operation. So for example, we've got an example here where we've got the same product being tested at multiple different insertions. It was at e-test, it was at wafer sort, it was at final test. And in final test, this particular product was reporting an electronic chip ID in the data log. So we can actually use that data, and we can bring that particular final test data, retrieve that data from our database, and display it effectively reconstructed in a wafer map viewer. Just a little bit about the performance of this. There were some questions once about sort of how much data do we have in this database, and is this typical performance? In previous years, we would run this demonstration over the network, connected to a bunch of servers. We've done a lot, though, in the last couple of years to enhance the performance of the application and shrink it down very significantly. Believe it or not, everything you're seeing now is actually running on this laptop, including all of the server components, the email components, everything else. We have a database here running, the SQL Server database running here with 8,000 lots of data in it, some 30 million parts, and approximately 20 billion measurements. All of that is in the database, and what you're seeing here is live retrieval of that information onto the client. In previous years, we've done this over the network. You've seen that the performance is more or less the same. The data is highly optimized. The data retrieval process is highly optimized, and we can handle very, very large volumes of data. Now, when I'm looking at this particular example, if I'm just looking at this particular wafer, for example, obviously the yellow areas that we can see in the wafer are the parts that failed at wafer sort, because again, what we're looking at here is final test data that's being mapped onto a wafer map, reconstructed on a wafer map. If I look at these couple of wafers, everything seems to be okay. But the system can also perform stacking of wafer maps. Here, for example, I'm looking at a stack of the yield of the 25 wafers in this particular lot. And I can see that there is a clear process pattern appearing here, which I should have been able to catch at wafer sort, but for some reason is actually making its way all the way through to wafer sort. Now, I can change the view or the way that I look at this data, and instead of looking at one particular wafer, I can ask the system to show all of the wafers in that lot. So now I can see all 25 wafers, and although I looked at 1 or 2 wafers and they looked fine, I can actually see there's a whole set of different wafers here which actually do show a very clear pattern along the edge of the wafer. So that obviously there's something going on here that I need to deal with. In addition to that particular pattern, if we go back to the consolidated view, okay, we can also see these additional stripes. I don't know if they can be seen clearly, but there are these additional stripes running through the wafer here. This is actually showing us that there's some kind of probing issue, that during probe, possibly, for example, a probe card alignment issue, it seems to be damaging some of the dies. You've got sites 1 and 2 on the probe card, or sites 7 and 8 on the probe card, seem to be damaging the parts, and that is being reflected only in final test. These kinds of issues you can only see when you can stack data from final test back on a wafer sort. So if you have products which are using chip IDs, these kinds of capabilities are extremely powerful. And we're already building sets of rules that can actually discover these kinds of issues automatically and alert you when we see these kinds of signatures, so that you can actually try and catch them at wafer sort and prevent the parts from reaching final test. Okay. So what we've talked about so far is everything to do with escape prevention, and also how we can use cross-operation capabilities in order to increase the quality of the data that we're dealing with, or the quality of our parts. What I want to do now is I actually want to recap and go back to something we did demonstrate last year for people who weren't here last year, and this has turned out to be one of the really key capabilities for our customers when we go back to traditional yield issues and utilization issues. One of the questions we get asked a lot is, I work in a company with hundreds of different products. Each of those products is running multiple operations, and each of those operations, at each of those different operations, we've got different yields. Okay? Now, how can I configure the system to catch a situation where a wafer or a lot has lower yield than usual, and send an alarm without actually setting up an individual rule for every single product or every single test program that I have? Because obviously, a product which is in early stages of its ramp will typically have low yield. Let's say 60, 70% might even be considered good, whereas a product which has been running for some time should be at the 95, 98, 99% yield level. And of course, if you receive 60% there, then you're going to really start worrying. So we can do that using what we call baseline rules. Baseline rules are rules that calculate what should be the expected yield for the population they're looking at automatically. So here we have a rule which is called the yield monitor rule, and here it's been configured to look at absolutely everything that's running through wafer sort, no matter which product. Okay? The configuration for the rule tells us that it's going to use a limit type of baseline. We could have simply set it to percent, and percent means, I'm going to say 90%. If it's less than 90%, send me an alarm. But the baseline allows this automated calculation. If we go to the advanced mode here, okay, in the advanced mode, we define or configure exactly how the baseline is calculated. So in this example, we are going to take at least the last 20 wafers from the same product, and up to the last 100 wafers. More than that is already meaningless from the perspective of a baseline. We're only going to take wafers where I have a significant amount of data. For example, if someone's just tested a few die on a wafer for engineering purposes or whatever, we're not going to use that wafer in our population. And here's really the key feature, is we're going to tell it to only use wafers that belong to the same product and subproduct that our incoming data log belongs to. So if there's a situation where, for example, where we're receiving data for a newly ramped product, we're going to use 20 wafers of information just from that product, which will have probably a relatively low yield signature. Okay? Now, we also have the option to set the rule to treat each test program as a different population as well, but actually we don't recommend using that option, because it's extremely convenient by leaving that checkbox blank. What we can actually do is we can catch situations where a new version of a test program is having some kind of significant effect on yield, either upwards or downwards, which again would typically mean that someone's written some kind of bug into the test program, okay, or dropped a test that was essential. The user here has a lot of control over the math being used to define the centerline function and the spread function that are used to calculate the baseline yield for this particular product. And we can skip straight to the email that comes as a result of this particular rule. Okay, so this is the rule that was triggered for a particular product. The system tells me that this particular wafer had a yield of 85%. If I scroll down, what I can see is that the calculation based on the center line and the spread and so on meant that this wafer should have had a yield of at least 89%. In other words, this is a significantly low-yielding wafer. And again, we have the links and all the ability to go from the mail back into OT Portal, bring up the wafer map, drill down into the bin data, drill down into the parametric test data in order to try and understand what has caused the issue. So what we've seen so far, summarizing both the yield rule and the escape prevention rules, is we've seen rules that are triggered when a data log arrives, okay? Or in some cases, they can be triggered when running in real time on the tester. Now, the question is, what else can we do when we've got all of this data in the database and we want to try and ascertain if there are additional patterns in that data, which you can't detect just by looking at a particular data log file? So for example, test time comparison rule, or what we call a cross rule. The cross rule is a generic rule that enables us to take any measure that we collect over any population in the database and determine if it is statistically different from the rest of the data. For example, in this particular case, we've configured the rule to look at a measure called good test time. It's going to trigger once a day. This one's not triggered by incoming data. It's triggered on a schedule. We've selected it to look at the good test time measure, which is something that we calculate based on the information in the data log, the average good test time for the part. We can tell the system to use this particular rule, in this case, to compare testers, but in the same method, in the same way, we could be using it to compare probers, probe cards, load boards, etc., any kinds of equipment. And of course, we can set up multiple rules to cover all of those different scenarios. And we can also tell the system how to treat different groups of data. So for example, by product, by operation, by test program, or whatever, to make sure that the data, again, is coherent and makes sense. So once I've set up a rule like that, and it triggers, again, we'll go straight to the email, save the simulation stage. Okay. This is an example of a trigger that this rule would send. And again, this is something now that if you think about it, it's looked at all of the data from the last 24 hours, and it's ascertained that I have a problem, in this case, with 6 different testers on 5 different products. Okay? And here at the top of the table, I've got a summary which is explaining which testers and which products currently have some kind of test time issue. Let's go scroll down here to the last example in the email. So here we have an example, for example, for the product called Condor. You can see it split by groups, product equals Condor. Okay, it was tested on 5 different testers. Each of those testers was testing anywhere between, you can see, 30, 40, 100, 160 lots. And we can see that the average test time on tester number 33 was over a second longer than the test time on the other testers. Now, of course, this is something I want to deal with because it's costing me money. I'm paying for test time. And this tester is just running slow. It's costing me low throughput and so on. We can bring up the data from, again, just by clicking the link in that email, we can bring up the relevant data from our database. And here, for example, it gives us automatically a box plot showing us the distribution of test time across those different testers for this particular product. And this is a clear example where it wasn't caused by 1 or 2 slow lots or something like that. You can see very clearly the entire population is significantly, for that particular tester, is significantly above the averages for the other testers. I can see this is a clear outlier, and I can now go contact the subcon and try and understand why is that tester performing so much slower than all of the others. One more example we have to show, and this is no longer related to rules, is another advantage of having all of this data available in the database. The data we collect can give you an extremely accurate picture of the performance of your organization. Taking this up now to the management level, okay? Think about it. You've got all of the data logs. We don't just know what you think the average test time was going to be for your products. We can tell you exactly what the average test time for your products was going to be. We don't tell you roughly what the yield should have been based on some kind of statistics. We can tell you exactly what the yield was. And then we can bring this up into this kind of dashboard view, and again, these views are highly customizable. In this particular case, we integrated with a customer with an existing BI system that they have, and there are several of these systems, for example, things like IBM's Cognos or PeopleSoft, Agile, various products that contain the key performance indicators, the KPIs that the various organizations use. We actually have a system now that allows us to import that data into our database. And of course, this is time-sensitive data. It can change as time progresses, weekly, monthly, or quarterly, or whatever. And we can then show our managers a very clear dashboard with stoplights, green, yellow, red, or gradients and so on, charts, etc. We can show them exactly how their products are performing against their baselines. And of course, this is an extremely useful tool for planning departments. Okay, you think you know what you can ship. Can you really ship it? Well, let's go and have a look at the data, and from there we can understand. We're beginning to see a lot of use in some of the organizations where senior managers are actually pulling up these dashboards in weekly meetings and then asking their engineers to explain why some of those colors aren't green. And of course, that has also driven up the usage of the tools very substantially, because all the engineers are spending their week going through these dashboards in advance to make sure that everything's going to be green. And the overall impact is a very significant impact on the efficiency of the organization, on the planning capabilities of the organization. What we've seen over time, and again, Craig from NVIDIA and our previous presenters from other companies in the last few years have talked about this a lot. It has a huge impact on yield. It has a huge impact on efficiency. It has a huge impact also, of course, today now on quality as well. Now, over the next year, as Craig hinted, we're going to be dealing with we're going to be delivering a bunch of new capabilities, for example, the virtual test capability that he described, and some kind of quite a powerful scripting environment and analysis environment to help automate a lot more of the tasks that we're doing here. So come back next year. We'll be making, I think, a very exciting presentation about that, where we'll show a lot of new capabilities and really building on the data feed forward capabilities, all of this capability to take data from one operation to the next, to combine information from different areas, parametric tests, wafer geography, e-tests, and so on, in order to build a very clear quality picture about every part that we're shipping. That's my presentation today. Thank you very much. If there are any questions.